Welcome. Today we're going to go over the how to solve conservation of momentum problems. So let's just start with how we're going to divide up this unit, right? So um, we have two kinds of problems in the impulse and momentum unit. One is where there is an external force applied, okay? And one of the ways to tell that there is an external force applied is that they actually use the word force or impulse, okay? If there is an external force applied, you need to use these ideas to solve the problem. But if there is no external force applied, okay, this is what's called a closed system. Okay, this is also where Newton's third law of action reaction really is obvious in a closed system. So that's the other place we talked about systems, right? And in a closed system, there's no external forces applied, and therefore the law of conservation of momentum applies. Okay, all right. So the technique here, well, so here's the formula on your reference tables. Okay, so we're going to kind of focus in right on this section here. All right, and then the words are defined here. Okay, so these are our formulas, and the one we're going to concentrate on today is this that says momentum before equals momentum after. Remember, little p means momentum, not to be confused with big P, which is power. Okay, or as Xander called it, momentum. All right, so here we go. The momentum before is equal to the momentum after. And then remember, the formula for momentum is mass times velocity. Okay, so here we go. Here's the idea. If you determine that momentum is conserved because there's no external force, the first thing you need to do is draw a before and an after picture. Okay, people get into trouble when they only draw an after picture, for example. All right, draw a before and an after picture. Use the picture to keep your data straight, and then you're going to write some version of momentum before equals momentum after, okay? And here is an expanded version of that, okay? All right, so let's just kind of quickly, I'm going to go over it here, and then I'm going to do it step by step, okay? So we're going to look at three kinds of collisions in this class. Perfectly elastic collisions, okay? So what we have is a ball. You can think of this like the cue ball in a billiards game, right? The cue ball comes along, hits the 8 ball, right? Afterwards, one stops, the other moves in this case. So to write the formula, we say, well, we have two objects before and two objects after. So I've got MV plus MV equals MV plus MV. Okay, let me kind of show you what I mean by this in a systematic way. All right, so this sheet here can be found in the momentum module, all right, and also linked in the information section for this video. All right, here we go. So in a completely elastic collision, let's imagine we have ball A moving and then it's hitting ball B, which is at rest, okay? First, we've drawn a picture, which we've already done, okay? And then what I'm going to do is I'm going to put a little MV under each object to represent its momentum, okay? Because P equals MV. All right, now, the law of conservation of momentum says the total momentum before will equal the total momentum after. So I'm going to sum up the befores and sum up the afters and set them equal to each other. Now I've gone from a picture to an equation. But here's the thing. I have different masses and different velocities. So to keep this straight, people often use subscripts, okay? This is how you could do that. So this is object A, and this is velocity A, and this is mass B, and this is velocity B. This is mass A, and this is velocity A. But the new velocity is different than the old velocity. So we make a little tick mark here. Sometimes we call that prime, all right, to distinguish between this, the velocity before, and the velocity after. And then here I have B, and again, this is the velocity after. So this is my formula written with subscripts. Now, I don't care if you put the subscripts in. Sometimes I encourage people to be kind of sloppy, not bother putting in the subscripts, and use their picture to keep the data very straight. It's up to you whether you put subscripts in or not. But if you're sloppy and don't bother to put in subscripts, just realize that this mass is not the same as this mass, and that none of the velocities are likely to be the same. All right. Now, let's imagine you're getting kind of this like a rear-ended. So you're moving slowly, and then we've got Speed Demon behind you, and they rear-end you. All right. We still have two objects before and afterwards 2 objects. Okay, so I'm going to sum up the objects before and set them equal to the sum of the objects after. And again, if I want to, I can put in little subscripts to keep this straight, or I can be sloppy and use my picture to do the subscripts. Okay, now, in completely inelastic collisions, the objects stick together afterwards. Okay, so you could imagine maybe like this is a ball of clay and this is a regular ball, and then they stick together afterwards, right? So I have 2 objects before, and I'm going to call this one object because these are traveling together. Okay, and I just decided to put a big M here just to remind myself that this is the mass of both of these things. I sum up the same ideas. Total momentum before equals total momentum after, except since these are moving together, I'm going to consider these as one object. All right. If I want to put in subscripts, I do this. And then I'm going to call this mass AB and this velocity AB prime, or AB after. All right. Now, most collisions are somewhere in between. Like, really, billiard balls are pretty close and bouncy balls are pretty close to elastic, but truthfully, only at like the molecular level with atoms colliding and electrons colliding with photons do we actually see a perfectly elastic collision. So most collisions are somewhere in between. All right. So let's imagine you get rear-ended, but somehow or other, the rear-ended person bounces back and you're forward. But the way we set up the formula is exactly the same. MV plus MV equals MV plus MV. And again, if I want to do subscripts, A, B, B, A prime, B prime. All right. Now, what about recoil? Recoil is when you start with one object and you end up with 2. So guns are really good example, but also like jumping off of a boat, all right? Or a raft is an example of recoil, okay? Now, you can't see, but there is a cannonball in here, okay? All right? So in the beginning, I'm going to say that we have one object, okay? And again, kind of like I did here, I did a big M just to remind myself that this is the mass of 2 things. All right, I'm going to move this down a little bit. And then afterwards, I have 2 objects, the mass of the momentum of the cannon and the momentum of the cannonball. Okay? If I want to put subscripts in, I could call this AB and AB. All right, and this is A, and this is B, and these are prime. All right, if I wanted, actually, I could have done cannon and ball instead of whatever A is, but whatever. Okay, all right. And then keep in mind that this mass is the mass of both the cannon and the ball. All right. Now, set equal. The last thing I want to just mention is that momentum is a vector quantity, and we could be asked to do a momentum in 3 dimensions. Okay. I am not going to go over how to do that, but except to say this. It's kind of like this. MV equals MV plus MV plus MV. But we now need to do it twice. Once for the x direction. Actually, we don't have to worry about the x direction of the mass because mass is not vector. And then we do it again for the y direction. So it's the same exact formula. Except we need to do it twice. Prime, and if we wanted to, we would, could put subscripts in here. But here's the key. The momentum is moving in both an x direction and a y direction based on those velocities. And if we had 2 dimensions, we would have to do this twice and then use our vector rules to come up with that. But that's beyond the scope of this course, so don't worry about it. Now, how do we actually do this with math? I'm going to do the first problem for you on the homework. All right, here we go. So I have 2 trains, and then they're going to connect afterwards. Okay, so here's what I'm going to do. I put a little MV under each object. And I'm going to, since these are stuck together afterwards, I just do a single MV. Sum up the momentums before and after. Okay, all right. If you want, you can put in subscripts. So A, B, B, AB, AB prime. Okay, now let's actually substitute in. All right, so mass They tell you that both the railroad cars have a 10,000 kilogram mass. So this is 1,000 kilograms times the velocity of 20 meters per second. This is vector, so make sure you're paying attention. Things that are going positive should be going up or right, negative down or left, or at least be consistent from your problem. Okay, plus, now, since this is going at zero velocity, this whole term drops out, but it's really important that it be in your formula because you need to account for all the masses in your formula, okay? So you can put in a zero here, but make sure that the formula does account for train B. All right, equals the mass. The two masses together are going to be the 1,000 kilograms of A plus the 1,000 kilograms of B times VAB prime. All right, so if I drop units, I get 20,000 over here equals 2,000 VAB. And if I divide by both sides, I get that the velocity of AB after is equal to 20,000 over 2,000, so that's 10. Now, the unit is meters per second, and let's just talk for 1 second about units. Remember that momentum is measured in the unit for momentum is, I'm going to go back to this. You simply carry it through. So the unit for momentum is a kilogram meter per second. All right. Yeah, just keeping that in mind. All right. Good luck. A lot of these problems are very similar, and then there is one recoil problem.